Hello, and welcome to lesson 15 of this introduction to calculus with Wolfram U. The topic for this lesson is linear approximations. So let's begin with a brief overview of this lesson. So you may recall that the derivative of a function is calculated by zooming in on it with some limits. And typically you take some limit as, let's say, h goes to 0 or some other variable. And the point is that as you get closer and closer to the desired point, then the function begins to look like its tangent line. So, for example, here's the function f of x equal to x squared, and that's the function. That's a tangent line. And you can see that very close to the point 1 comma 1, they both look essentially identical. So you can use this property to approximate a function near a point with its tangent line. And that's a dramatic simplification. After all, a curve is a rather complicated object, and a straight line is perhaps the simplest of geometrical objects. So if you can replace a function with its tangent line, that's great. And that's the topic of this lesson. Namely, we'd like to talk about linear approximations, but we'll also talk about so-called differentials and some of their applications. So let's begin with the topic of linear approximation. And you may recall that the tangent line at a point x equal to a is given by an equation of that type. Now, the y over here is a point on the tangent line, but what you could do is to replace y by f of x, the function itself, and then you get an approximate equality whereby the value of f at x can be approximated using its derivative at the point a. And this approximation is called the linear approximation of f at a, because the tangent line is being used to approximate f. So here's the picture. You have the function and you have tangent line, and that tangent line is now called the linearization. So linear approximations are a very important tool in calculus. And as an example, let's take this function f of x equal to square root of x plus 8. And what we want to do is to approximate the values of the square root at 8.98 and 9.03 using this function. Now, obviously, when x is 1, the square root of 9 is just 3. So what we do is we work near 1, and you get back f prime at 1 is 1/6. And now you set up the equation of the tangent line. So tangent is equal to 3 plus 1/6 of x minus 1, and you get back the tangent expression. Now, when x is 0.98, you are at 8.98, whereas when x is 1.03, then you are at 9.03. So you can use the tangent line to approximate the values over there, and those are the square roots at those 2 points approximately. So here's the picture, and in the picture you see you have the function, the linear approximation, and the values at the nearby points. And you can see that the approximation are very, very close to the original function, though of course they are not exactly the same. Okay, the question now is, how accurate is that approximation? So suppose you want to have an accuracy within 0.5 units. Well, here's the equation. That's the exact expression. That's a tangent, and you want that difference to be less than 0.5. So what you can do is set up an equation with the reduced function and solve, and then numerically the values lie between negative 6.3 and 14.39. So as long as you stay within that range of x, you'll get an approximation which is correct to within 0.5 units. Now, let's say you want to increase the accuracy to be less than 0.1, then you set up the equation with 1/10 over here, and you get back the values. In this case, you have a much tighter range from negative 3.04 to 6.2 roughly. Okay, so in physics, one needs this notion of linear approximation all the time. So, for example, when one studies the pendulum and you want to talk about the period of the pendulum, you start with the equation for the acceleration. So that's the tangential acceleration at, and g is the acceleration due to gravity, theta is the angle that the pendulum makes with the vertical. And the point is that when you're very close to 0, then sine has got a slope of 1, because cosine of 0 is 1, and the value of sine at 0 is 0. So near 0, when theta is very small, the sine of theta is approximately equal to theta. So if you replace the sine theta over there with the theta, then you get back a much simpler equation, and that's the one that's used in physics textbooks at the elementary level. As you go more advanced, of course, you might want a better approximation. So here's a picture of the actual acceleration, the curved one, and the linear approximation. And of course, you see that they are both very close by, as long as you do not go very far away from 0. Okay, so a related notion is the notion of a differential. So to understand that, remember that the derivative is sometimes denoted as dy over dx. Now, dy over dx is the same as f prime x. So if you kind of cross multiply, then you get the equation dy equal to f prime x times dx. And these quantities dx and dy are called differentials. So they represent the change in x and the change in y respectively. And so, of course, if you're given dx over here, then you can work out dy using f prime x. So that's like a small machine where as you put in different dx's over here, you get different dy's over there. So here's the picture. The picture is that as long as you stay close to x over here, then you can use that approximation to find the change in y. But of course, that's still approximate. And so the question is, how does that relate to the actual differences? So here's an example where you have a function, and the problem is to work out df, the approximate change, and the actual change when x goes from 3 to 3.05. So let's first work out the exact change using subtraction. And now here's the approximate change given by df. And you can see that they're pretty close to each other. And in general, that's the equation for the change in f when you make a small change in x. And here's a picture of the function and its approximation. And you can see again that as long as you stay close to 3, the approximation is quite good. Okay, so the question is, why are differentials important? And the reason why they're important is that sometimes you may not be able to find delta f, the actual change in f, exactly, and then you might as well use differentials because they are really quite helpful and easy to work with. And in fact, what you're talking about over here is exactly the same as linear approximations. So here's the equation for a linear approximation in the differential language. So the value of f at x plus dx is the value of f at x plus f prime x times dx. So as an example, here's the function square root of x plus 8 again. That's the differential. You plug in a value of negative 0.02 for dx, and then you see that it's pretty close to the value of the function at 0.98. So the point is that differentials are just another way of talking about linear approximations. Okay, so one important place where they are useful is when you want to estimate errors. So, for example, suppose that the radius of a sphere is 11 centimeters, and you know that the error in measurement is about 0.1 centimeters. And what you want to do is to find out that the maximum error when you calculate the volume of the sphere. Now, the volume of sphere is 4/3 pi r cube. So you differentiate that equation. Now, volume prime is the same as d volume over dr. So you can rewrite the equation as d volume equal to 4 pi r squared dr. And then because r is 11 and dr is 0.1, that's the error, you can work out the error in the volume. And it turns out to be 152 approximately. Now, that looks like a huge number. So the question is, why is it so large? Well, the point is that you really need to talk about the relative error over here to understand what's happening. So the relative error is the error divided by the actual volume, and then that is just 0.027. So of course things look much better than they did before. Now, if you do not plug in the value of r over here, then the relative error looks like 3 times dr over r. But that's just 3 times the relative error in the radius. So that says that the error in the volume is 3 times the error in the radius, provided they talk about relative errors. Now, the other way to talk about these errors is to use a percentage error. So the percentage error in this case is 2.7 for the volume and 0.9 for the radius. Okay, so that brings us to the end of this lesson, and the main point is that linear approximations are very important in mathematics and science, and all that you do in such a case is to replace a function by its tangent line. And as long as you stay close to the point, then the approximation is very close to the actual function. And one place where you might find them really useful is in physics, but of course they are also useful in chemistry and in economics and in finance. Wherever you go, you will find the need to use linear approximations. And another way of talking about these approximations is to use differentials. And those are particularly useful when you want to talk about errors in measurements. So that brings me to the end of this lesson, and the next lesson will talk about maxima and minima. But before doing that, we will have a problem session to go over some examples for errors and approximations, and then we'll get back to maxima and minima. So I hope you found this lesson useful. It's a very important lesson. Do review it and be ready for the next session. Thank you.